Yeah, I would like to thank the organizer for putting together an amazing workshop. So this is joint work with my student Stefano. Yeah, so unfortunately couldn't be here today because he was waiting all night because of the noise deadline today. So the motivation for for this work comes from the kind of dramatic increase in the past few years in the capabilities of machine learning based prediction models with which provide now quite highly accurate prediction, and this has led to major breakthrough in a number of different domains. And so one of them is, for example, proteomics, with, for example, the Google prediction system, so AlphaFold, that is used to so from data of amino acid sequence to produce some prediction of the protein structure. So if you got as input data some amino acid sequence, so you get some prediction here. So yeah, before AlphaFold, so over 60 years, so using experimental methods, people managed to identify the structure of about 170K proteins. So it was quite expensive. And as of July 2022, so the AlphaFold protein structure database was 200 million proteins from 1 million species. So that's the game changer in the field. And so, yeah, because of this, and yeah, progress in other fields. So, there has been a strong incentive in trying to use these ML predictions as imputed data when you are in settings where the data are quite limited, very costly to acquire. And one of the challenges is, how can you retain some valid statistical properties without making really any assumptions on this machine learning model. So these ML models usually they are very, very large, very big black box with a lot of parameters, and they come without any sort of guarantees. So the setup I'm going to consider is the following. So we assume that we've got some input-output pair xy from some distribution P, and I've got little n labeled observation. Okay, so xi, yi, iid from P. And I assume that I also have a set, capital N, of unlabeled observation that will be denoted x tilde y, so from the same marginal distribution Px. Okay, and I assume that capital N is typically much larger than little n. Okay, and with that is given some black box machine learning predictor f. Okay, so f is going to be fixed. I'm not going to update it. And yeah, it might come from fitting a much larger data set, but I've got no information on f. And so for a convex loss L theta of xy, so my objective is to estimate the parameter theta star, which is the argmin of the expectation of the loss. So under some regularity assumption, so the solution theta star is the solution of an estimating equation as defined by Martin Plummer yesterday. So my aim is to derive some estimator of theta hat of theta star, and derive also some confidence region for this parameter that has the right frequencies, guarantees exactly or asymptotes. For the sake of this presentation, I'm going to focus on a very simple example. To keep the notation simple, so my loss will be just the square loss, and theta star is just the expectation of the output on a variable, so expectation of. So the classical estimator, so if you were not to use the machine learning prediction, would just be the sample mean on the label data. It's one of the answer of my co-one of the yi. And the estimator that you would use, so this one would have relatively high variance because little n is assumed to be small. If you were to try to use your powerful machine learning prediction, the imputed ML estimator would be the sample average when you would average over your actual observation yi and the kind of imputed observation f of x tilde I. Okay, so this one would have a low variance because capital N is typically very, very large. But of course, you've got no guarantee at all because you don't know anything about this prediction. Yeah. So one way to is Stefano is hi Stefano. So one way to deal with this is some prediction powered inference, which considers the following decomposition. So you write theta star as the sum of the expectation of f of x plus the expectation of y minus f of x. So the first term, m, can be estimated very accurately. Okay, we've got a lot of unlabeled observations, and so we can estimate m very accurately. And the term, so expectation of y minus f of x, so delta is called the rectifier. And so this accounts for the discrepancy between your predicted output and the true output y. So yeah, the key is to estimate this rectifier. So in the standard PPI framework, so you use for lambda as an estimator, so the using only the label data. Okay, so the sample mean of y minus f of xi on the label data, and you derive so asymptotic confidence intervals based on the CLT for delta. Okay, so these confidence intervals are combined with those from M to obtain a confidence interval for the parameter of interest with theta star. Okay, so one of the key here is that if the predicted output f of x is correlated with y, then PPI is going to provide more accurate predictions and shorter and valid asymptotic confidence intervals. Okay, so that there's quite a lot of related work in statistics and other fields. So in particular from semi-parametric inference with nuisance parameter, related work on double machine learning, missing values, service sampling, causality, and the estimator that we obtain in the end is a control variate estimator, which has a lot of use in, for example, Monte Carlo. Okay, so PPI, typically uses the sample mean to estimate the rectifier delta. So one thing that we wanted to consider is that, ML predictions are typically extremely good. Okay, so what we often expect is that the prediction are going to be accurate, and so delta, the rectifier, should be in general setting quite close to 0. But at the same time, it's also prone to catastrophic failure, and so it can be also arbitrarily large. Okay, so what we would like to do is to try to incorporate some sort of prior information to take that into account. So of course, Bayesian methods are appealing here, but if you were to then use credible intervals, so as Peter Winbal has shown, so credible intervals are not going to, you're not going to get your frequentist guarantees, and so the objective here is kind of the same trade-off as in the previous code. So you want to add some Bayesian structure, but retain the frequentist guarantee. Okay, and this is where Pratt comes in. Okay, so this is John Pratt, who was professor at Harvard, who should be around 93. And so he's got early work from, let me see all the way from here, the but he's got early work from 61, 63. And so the setup is the following. So you assume that you have got observation yi from some parametric distribution p beta, and you want to get some confidence interval for the parameter beta. And so the idea is to minimize the base average volume subject to 1 minus alpha coverage from every beta. So you try to find the confidence interval C alpha n that minimize this expected volume under some prior pi under the parameter, such that you have the correct frequentist 1 minus alpha cover. So the general idea is that you've got your alpha budget, okay, and you want to spend it wisely where the prior thinks it matters the most, and so you've got some sort of efficiency. So if the prior and the data agree, you obtain tighter confidence regions, and when there is a conflict, then you get larger confidence regions. But you have the same guarantee. So because of the construction, you've got a valid frequentist properties. So this was developed in the 60s, but there has been a renewed interest in the past few years. So in particular, with work from Peter Hoff and collaborators, and so this approach and related approach have been called so frequentist assisted by Bayes, so FAB. Okay, so I've shown here some illustrations. So here you have as a function of the observation y. So the corresponding, so the dashed line is the standard confidence interval. And in the orange line is the Pratt confidence interval, so using a normal prior centered at 0 for the parameter of interest. So on the right-hand side, I've shown the volume, the width of the confidence interval. And so what you obtain, so this one is the standard one, so the width is independent of y. And if you had a prior which is centered at 0, so the width will be smaller than the standard confidence interval when the prior agree with the data, and otherwise will be larger. Okay, and so in this case, yeah, you can the volume is not bounded uniformly in terms of the observation y. It can be arbitrarily so to draw some connections with the previous talk, so Pratt showed via what is known as the Gauge-Pratt identity and Niemann-Pearson lemma that if you solve this optimization problem, so the interval is of the form the set of beta such that so p tilde n of y1 to n over the product over I of p beta of yi is less than some value k of beta. So where here, so p tilde is the marginal likelihood under the prior phi of y1 to n. Okay, and at the denominator, you got just the likelihood for a parameter beta, and the threshold k of beta is the smallest value such that you got the coverage conditions holds. Okay, so it has the form here, as you recognize, of a likelihood ratio. Okay, and yes, Val just explained. So this is a non-negative martingale, and it's also a process. If you see it as a function of beta, the inverse is also in posterior, and so by Bill inequality and the method of mixture, so you can also show that if you replace k of beta, so the smallest value, just by 1 over alpha, then you obtain a confidence sequence, which is now anytime valid, so which is valid for any n greater or equal to 1. Okay, so one of the conclusion between that is is that too many things on this slide. So Pratt's confidence interval is always included into the anytime valid Bill interval. Okay, so any information we have about Pratt interval means that this is also included in Bill's confidence. Okay, so the idea is to now use Pratt's approach for the construct confidence interval for the rectifier delta in PPI. But yeah, there were two things that were kind of puzzling us using Pratt. So the first one is, okay, so you've got this confidence region. What do you use as an estimator? Or you could use the midpoint, but is there a natural estimator with this approach? And the second thing is, can we use prior? So we've seen that if you use the Gaussian prior, it can get arbitrarily large. Okay, and we know that those machine learning methods, they can be catastrophically bad. So if you get something that is that can be extremely large, that's not very good. Can we get something which is uniformly bounded, where the width is uniformly bounded, even in the case of the conflict between the prior and the data? So the thing that we've looked at is that we've shown that if you take a natural exponential family, then the posterior mean of the natural parameter is always contained into Pratt's confidence region. Okay, and so in particular, if you take a continuous likelihood, as alpha goes to 1, your confidence interval shrinks to a single point, which is the posterior. For Gaussian likelihood, okay, so building on earlier work from Phil from 73 on conflict between posterior and priors. So if the prior has the power rotates, then your confidence region reverts back to the classical one. Okay, so the effect of the prior essentially vanishes in case of a conflict if you use a prior such as a student or prior. And then we combine the fab with using this property, so with prediction power of inference, in order to allow the addition of prior information on the quality of machine learning. Okay, so this is an illustration of what you get now if you use prior with heavy tail. So I still have my standard interval with the dash blue. In orange, this is the Gaussian prior, and all the other ones are different types of prior with power law attacks. So if you look on the right, so here as a function of y, so the volume of your confidence region. So for all the different methods, so they are all centered at 0. So when the data agree with the prior, then you obtain tighter confidence intervals compared to the standard one. When you start to disagree, then you become worse than the standard approach. But so in the case of a prior with polynomial tail, as the conflict increases, then you just revert back to the classical confidence interval. Okay, so which means that the width here of your confidence region is uniformly bounded over y. This is this is nice, and now this is some illustration of the similar illustration using a plot. So this is a confidence curve that Peter Goldwald just introduced. So if you take a y section here, so over y this is the budget alpha. So if you take a section y, you get the endpoint of the confidence region. So here the blue one again is the classical one. So the top on the top, so you have classical versus different normal, where for each column, this is for different observation. So the first column, y is equal to 0. So you got agreement between the prior and the data. Then y is equal to 1, and the last one, y is equal to 100. So you got strong disagreement between the prior and the data. So if you take the Gaussian, so the dashed line here represents the focal points of the different methods. So it corresponds to the posterior mean in case of the Pratt approach, and just is equal to y in case of the classical. So for the Gaussian one, you obtain tighter confidence region than the classical one, and as y increases, you obtain something which is very large and where the focal point is very far from the observation. So on the bottom, you have the same for different prior with power law tail. So you got the same behavior as the Gaussian when there's an agreement with the data with tighter confidence intervals, and when there's a strong disagreement between the prior and the data. Okay, so the scale is not the same between those two. here you just revert back to the classical setup. Okay, and the focal point here is always the posterior. Okay, so we use this this approach, so the FAB approach. So we wanted to use something that was quite tractable. So we used prior pi on the rectifier delta. Okay, so it has polynomial tail, so it has the property that that we wanted, and so we get confidence region on delta, and then combine them with confidence region on M to obtain confidence region on the parameter of interest. So we consider different data sets that were used also in the original PPI paper. So one from using AlphaFold predictor for modeling protein residue. So one on using an ML method, so gradient boosted tree, to predict, to estimate the fraction of Amazon rainforest loss to deforestation, and another one to predict, estimate the proportion of galaxies having spiral arms, so using some deep neural network. Okay, so in each case, so we report, on the larger data set, we estimate the true value, which is represented by a dashed red line. And so here you have in blue, the confidence region over 5 applications for the classical method, in orange for the PPI++, and in green, so the one that introduced some prior information. Okay, so what we see here is mostly that you get the right coverage. And if we look more closely at in terms of the width of the interval, so here as a function of n, so the number of labeled data. So I've shown here the second plot is the volume. So we see that the PPI prediction power, so the one that uses the unlabeled data, so improves over the classical, and using this prior information, we go closer over PPI. And the bottom plot so shows the coverage, so showing that we got relatively good coverage at least when n is large. Okay, so here, in these talks I've discussed further properties of FAB or Pratt's method. So in particular, identify what is the focal point of Pratt's confidence region, and discuss the properties of the impact of the prior on the width of the associated confidence region, and to discuss some bias-assisted method for inference with black box machine learning prediction. So we've shown that we can provide the shorter confidence intervals if the ML predictions are good. If they are poor, then we just revert to the standard PPI by using the prior with polynomial tail. And in any case, so we got guaranteed asymptotic frequentist coverage because everything is based on the CLT for delta hat. So we got two papers on this. Now you might ask, okay, so we've got this kind of property for Pratt's confidence intervals, and there's a connection with confidence sequences. Can you do the same for confidence sequences? Valentin will tell you everything about it in his talk. And we also looking at so this will define finite sample size confidence region. So you might want to do also to do the same with confidence sequences, and so we're currently working on anytime valid bias assisted confidence sequences for the prediction parameters. Thank you.
Thank you so much. Maybe we have time for a quick question while we set up the next talk. There are any very quick